Hi guys, this is Wenjing, and today I will going to present our paper, which is focusing on the task scheduling and resource management in the MEC-enabled computing networks. So today's presentation contains 5 parts. So we will first briefly discuss about the background and motivation of our paper. Then we will present our proposed system model, and following by the algorithm design. And after that, we will demonstrate the experimental results that validate our theoretical results. And finally, we will conclude our presentation by present the summary of this paper. So let's start with the background. So we know the 5G network is very important for supporting a multitude of emerging applications that require rich data communication in both directions, such as AI and VR. And the properties of 5G network are that they can provide high reliability and also can support high volume data. So we know the AI and VR and applications like these require abundant computing resources. So that is the advantage in this scenario. And it seems like that cloud computing is a promising technique which can make the data processing be much more efficient. But obviously, there is a major limitation. That is, it can cause large communication delay. This is because the cloud center might be very far away from the user's devices. So to reduce this latency, the technique of multi-access edge computing, which is also a network concept, is a promising solution. And it has been received widespread attention from both academia and industries. So in terms of the academic research, recent works that are studied on multiple deployment approaches, joint radio and computational resource management and applications, they can take advantage of MEC. And on the other hand, in the industry side, several MEC-based architectures have also been developed, such as ThinkAir and Edge Gallery. In fact, so how can we achieve efficient computing power allocation and collaboration remains to be a huge challenge in the deployment of the MEC system. To address this challenge, our goal is to establish deep integration between the MEC and networking. So that is, we try to build the multi-access edge computing networks that are shorted for MECN. So in this slide, we will briefly describe the system model. So in this commutation offloading model, the transmit rate of task and energy consumption are given in these two equations. So first, we define the transmit rate of task on subcarrier, and then we also define the energy consumption in task N. And then we also define and model the computation time and the energy consumption at the MEC server side. So the data size of task N is defined as dt, and we followed by the definition of energy consumption by the MEC server while processing the task in temps.t as capital ET. Similarly, we also define two updates of the queue length. So the first one is the queue length of the task in the network update according to the first equation. So we can see the update will take the maximum of this value from temps.t and update the value of the queue length at the next temp step, which is temps.t plus 1. And followed by that, we also define the update of queue length qt on the server, and is defined in this equation. So in this work, we focus on the entire, and also we can see the total energy consumption of the task processing in the system, which include the energy consumed by transmission, the energy consumed while waiting, and the energy consumption of the MEC server. So accordingly, we define the system operation at temps.t as a variable capital AT, and also a vector that contains 5 elements, which are PT and rho T, SD, ET, and FT as the elements of this vector. So then the average consumption, so the average energy consumption minimization problem can be formulated as this minimization problem. And so before solving this optimization problem, we aim to use the Lyapunov technology to transform these optimization problems as follows. And the specify function is expressed in this way. So it's easy to see that this optimization is way more complicated. So to solve this problem, we actually develop a dynamic resource allocation algorithm, which is showing this algorithm 1. So basically, our proposed algorithm is based on Lyapunov optimization, and so this algorithm in principle contains 3 steps, and the essential step is the second one, where we need to obtain the network control policy that include the power allocation, sub-area assignment, commutation time, postponing time, and also the CPU cycle frequency. So these parameters we need to derive before we solving this optimization problem. So in order to solve the optimization problem mentioned above, we will first develop an algorithm for the power allocation and subcarrier assignment. So specifically to solve this, to obtain the power allocation and subcarrier assignment, we first fix the commutation time ET, and then the optimization problem of power allocation and subcarrier assignments will be given by this optimization problem. And C1 to C4 are the constraints that we mentioned above. And so to solve this optimization problem, we will introduce a new variable, and then we rearrange this optimization problem to a new one, and we prove the new optimization problem to be a convex optimization problem. Then we can solve this optimization problem by standard convex solution. So to obtain the computation time allocation, we will fix the parameters PT, ρt, ft, and st. And after that, the optimization problem of computation time allocation will be rewritten as this new minimization problem. And we can observe that this optimization problem is actually a standard linear programming. So the optimal computation time can be solved easily. So next, we will derive the postponing time allocation. Similarly, we will also fix the computation time ET and then derive the minimization problem for solving the optimal postponing time allocation. And we can see that the object function is actually convex and the constraint is linear. So by definition of convex optimization, this problem is considered as a convex optimization problem. And so we can solve the we can derive the optimal solution by a standard solution of convex problem. So in this slide, we will compute the optimal CPU cycle frequency. And we also fixed the computation time ET and rewritten the optimization problem to find the minimization problem of CPU cycle frequency. And similarly, we can also see that both the object function and the constraint are convex. So we can also use a standard convex optimization problem solution to solve this problem and obtain the optimal solution out of this problem. And finally, we come to the simulation results. So as the results shown in these figures, we can see that figures 1 and 2 show the convergence of the proposed scheme, and figure 3 shows the performance of this scheme. So as the results show that compared with other algorithms, our proposed algorithm performs the best in terms of average energy consumption and also the convergence time, and how fast the algorithm will converge. And our proposed algorithm performs better than the other ones. And finally, we come to the conclusion of our presentation, and we will summarize our work in the following 3 content. So in this paper, we have studied the average energy consumption minimization problem, where we jointly optimize the transmit power allocation, subcarrier assignment, computation time, and postponing time, and also the CPU cycle frequency for the MEC-enabled computing networks. Then we propose an algorithm that does not require any prior knowledge of the network in advance. In particular, the solutions of the transmit power and subcarrier assignments were derived by using the Lagrange dual decomposition method. And the solutions of the computation time, postponing time, and CPU cycle frequency were derived in closed form. And finally, the simulation results that validate our theoretical results show that the performance of the proposed algorithm can achieve a better trade-off between the average delay and average energy consumption compared with other algorithms. So thank you, and this is the end of our presentation. Thank you so much.